Hi, I'm Ahmed, and in this session, we will see the challenges we usually face in machine learning. So, challenges are of two types. One is challenges regarding models, and the second one are the challenges with respect to the data. First, we will see the challenges regarding model. So, first of all, think in this way like we have data, and data is always equal to information plus some noise, or you can say data is a combination of information and the noise. Now this noise can be from some mismeasurements, from some human errors or miscalculations, or from some sensors noise, and this noise can be some true values which are inconsistent with the rest of the data, but we cannot figure out that this noise is due to some errors or this is true values but actually far away from the rest of the data. Now the challenge is to identify the information content and distill away the noise. To do this, machine learning uses a train test approach. Now here we usually try to build such a model that can capture the patterns from the information and uh, usually try to ignore the noise. Now here we use train test approach. Train test approach is like we split our whole dataset into two parts. One is training dataset and one is test dataset. Let's say we have a 500 samples in a dataset, and we have splitted our dataset into two parts. Like training dataset has 350 samples and test dataset has 150 samples. Okay. Now we will train our model on the training dataset, and then we will test our model to see the accuracies and the results of the model. We will use testing dataset. Okay. If it is giving us a good result on the testing dataset, then we can say our model is good enough for has good accuracies. Now, what are the challenges regarding this? The first challenge can be a overfitting, and the second is underfitting. Now, what are these overfitting and underfitting? Overfitting is usually occur when we are trying to during our training process we are trying to or our model is trying to get the patterns from the data, and during the getting the patterns or capturing the patterns from the data, it should capture the information or the patterns from the information but not from the noise. But in case of overfitting, it also has captured the patterns or from the noise. So in this case, we usually call it as a overfitting, or the model we usually call overfitted model. In the second case, underfitting, when we are doing training, our model has not captured the patterns from the information. Okay, we call that our model is undertrained or is not good trained on the dataset. In other words, you can explain overfitting and underfitting or the difference between them. When you have trained your model on the training dataset, you have trained your model. Now, if you will test your model on the training dataset, it will give you a good result. And when you will test your model on the test dataset, it will give you bad results. This case we usually call as overfitting case. Okay, when it is giving good result on the training data points but not giving the good results on the testing data points, or you can say the testing data points are those points that our model has not faced or has not seen during its training process. In underfitting case, after the training of the model on the training dataset, if we will test our model on the training dataset, it is not giving us a good result on the training dataset and on the testing dataset. In case of overfitting, it is also giving a good result on the training dataset, but not on the test. But in case of underfitting, it is giving bad results on both cases when we are testing on the training dataset and when we are testing on the testing dataset. Now, our hope is that the model does the best on the testing data to capture all the information but leave out all the noise. So, these challenges usually we face in modeling, overfitting, and underfitting. Now, the challenges regarding data. There are multiple challenges. First, insufficient quantity of training data. It means that the goal that we are trying to achieve requires a lot of data, but we have not enough data. So we call usually insufficient quantity of training data. Let's say for a toddler to learn what an apple is, we just tell or we just tell to the toddler or teach to the toddler that by pointing out that this is a this is an apple, okay, and we will repeat this process multiple times so toddler can learn immediately. But in case of machine learning, the models are not so much intelligent. Okay, the toddler is more intelligent as compared to the models in machine learning. In case of machine learning, we usually have to feed a lot of data. Sometimes we need thousands of data points to train a model, or sometimes we need millions of data points to train a model. There is a paper published in 2009, The Unreasonable Effectiveness of the Data. This paper has explained that sometimes for some simple models and some complex models giving the same results. Okay, and the aim is to, or the main challenge is to have some enough amount of data. Okay, and or you can say in other words, this paper is explaining that data matters more as compared to the selection of the model. If I will show you, this is the model, the paper, sorry, the unreasonable effectiveness of the data. This the description of the paper, and the idea is that data matters more than the algorithms for complex problems. Uh, this paper was published by Peter Norwich in 2009. Okay, here these are the graphs for some models, and here the same the you can say they have explained by using graph that the some simple models are also giving the good result when fed we have fed a lot of data or enough data to the model during its training process. So this that's why they have called that unreasonable effectiveness of data. Now the second challenge we usually face is no representative training data. You can say this the goal that we are trying to achieve cannot be uh, possible in the case of the data that we have. We usually call as no representative training data. In other words, if I will give you some example, uh, let's say we have our aim is to let's say our aim is to predict the price of a house. Okay, let's say the price. Okay, so the price of the house. Okay, now here we have the columns. Let's say the column house number, the column the house is for sale or not, can be a binary like 0 1. This is price like 50,000, 60,000, 42,000. And here the house number like a 44 house number, 53 house number, 41 house number. Okay, now here you can see that the price um, is in for the context, or you can say for the conceptual way, you can say that usually price uh, have no relation with the house number. Okay, and the price is also have no relation with the for sale, or you can say these are the not good predictors of the to predict the price. So that's why you can say that is no representative training data. This data is non-representative that for the goal that we want to achieve. Okay, instead of that, if the data will be have like this the price here, and here instead of these two columns, if we have the column like a area of the house, and here the number of rooms, let's say number of rooms. Okay, in that case you can say that uh, these number of rooms and area can be a good predictors to predict the price, because number of rooms can have some sort of relation between price. Area also have usually have some relation with the price, like if the area is growing, uh, or you can say the larger the area is, the larger the price. Okay, so in this way, you can say this challenge is no representative training data. The goal that we are trying to achieve cannot be possible by the given data. Here is a good example: US presidential election in 1936. If I will show you here. Okay, so here this is a very famous example. The Literary Digest have conducted a large poll in 1936 when the election was between Lyndon and Roosevelt. Now, they sent a mail to about 10 million people and got 2.4 million answers, and predicted with high confidence that Lyndon would get 57% of the votes. Okay, according to Literary Digest, Lyndon will win. Okay, but actually, Roosevelt won with 62% of the votes. So the flaw was in the Literary Digest sampling method. Okay, let's say you, in that case, our target variable is to predict either Roosevelt will win or Lyndon will win. Okay, and on the other side are the votes. Okay, so usually in the population or the people, there are different classes. Some elite class people, the middle class people, and the lower class people, and all have some different opinions. Okay, all classes, all the peoples of categories, some all every type of people has some different opinion regarding the vote. Okay, so for the sake of prediction, usually uh, we usually try to capture the all type of audiences. Okay, so here there are two flaws in Literary Digest poll. We will see one by one. The first flaw was that they have obtained the addresses to send the poll to. The Literary Digest use telephone directories, okay, or list of magazine subscribers, club membership lists, and these sort of like these uh, sources. All of these lists tend to favor the wealthy people, and who are more likely to vote Republican. So, according to them, London, or according to elite people spotted the London. So that's why they got the answer of 57% of the vote. And the second flaw was that less than 25% of the people who received the poll answered. Like they have sent 10 million, the mail to the 10 million people. But out of 10 million people, they got the answers from only 2.4 million people. But what about the 7.6 million people who have not answered to the poll or the mails? Okay, they have uh, they have not considered the people that have not answered that. So this also sort of bias. So in this way, you can see that the problem here was a no representative training data. The goal that we are trying to achieve can for that we should have some uh, the some sort of data that is related to the target variable or our target. Okay, but if we have some non-representative data, then we cannot achieve the uh, our target. Or you can say the independent variables or dependent variables should be compatible to each other or should have some relation between each other so that we can use this data as a training process of our further modeling. Okay, so independent variables or dependent variable should have some strong relation with each other. So this can be a challenge if they have not strong relation with each other. Third challenge can be poor quality data. Poor quality data is like our data, training data has a lot of errors, a lot of outliers, noise. So we have to do a lot of treatment on that, and maybe let we will fall into some biased data. Okay, so poor quality data is also a challenge uh, in machine learning or in the regarding data. So last challenge can be considered as irrelevant features. Okay, like here, these are the you can see like here, if we have, let's say in that case, if we have here another column which is like house number. Okay, so here we have three independent variables like these three independent variables, and this one is dependent variable. So these independent variables, this area has some relation with price. You can think in the contextual way or conceptual way, and this number of room can also have some sort of relation with the price. But here you can say the house price, house number. The house number can be sort of this house number can be a sort of irrelevant feature. Okay, irrelevant feature. Okay, so this is also a challenge when we have a data set and there in usually we in our data set we have number of irrelevant features. So we try to figure out what features irrelevant features we have in our data set, and we usually or we should drop these irrelevant features before going for the training process. So uh, this session is about the challenge of the machine learning, and we have seen that challenges regarding the modeling and the challenges regarding we usually face in the case of data. Okay, so I hope you have enjoyed this session. So hopefully we will meet in the next session. So